It starts at infinity and ends at 0. But this one goes, okay, omega from 0.
Bless you.
Here is from infinity to 0. Okay. All right. So that's the Nyquist pattern. Everybody has the Nyquist pattern equations to describe it? Okay. So, I don't know. Should I take out the interesting?
Should you what? What was that?
I think the increase in my circle is pretty wild, etc. Just figured it out. But all right. So now that describes what the Nyquist path is doing. Now let's figure out what the Nyquist plot will be doing. So here is Nyquist plot. For C plus, S is omega I. So GOL of S will be GOL of omega I. Does that look familiar?
Yes.
What is the body plot of? Recall that body plot of U of G. So, okay, you can't read that. Right? S log omega goes from minus infinity to infinity, which means omega goes from 0 to infinity. Right? So, given any omega, this gives us the log of the magnitude, and this gives us the argument of the complex number GOL of I omega. What is now a very common transfer function we deal with? First order plus time delay, okay? Let's say, let's figure out what the Nyquist plot of C plus, the C plus part of the Nyquist plot would look like for, let's say, example, let's say, GOL, which is, let's say, with a proportional controller, okay? And first order plus time delay. So let's say I have GOL equals 12 over 5 s plus 1 e to the minus 7. Okay? What would be the body plot of this? The body plot of this, if you recall, I have low frequency. Remember the log AR when it goes to first order plus time delay? It goes to log of absolute value decay. So the log AR will be log absolute of 12, and it would be a corner frequency where? Where's the corner frequency?
-1 divided by 5? Log of that?
Log of 1 over tau, right? So it would be log
1 over 5?
1 over 5 for frequency. So it would pretty much stay here, and then it would have at that frequency slope minus 1. So this have the azimuth. And I gave you a pretty large delay. If you remember, for a large delay, we did the different delays. If it's a small delay, you see the minus 90 plateau temporarily, and then you go down. Okay, let's make it more interesting. Let's make it.
No.
Let's make it so you don't mess up your notes. Let's put a 0.7. Put a point. So the delay, sorry, the phase lag will start at 0. Would be a little bit below minus 45 here. Since the delay is more probably we'll be seeing this. And then it would continue going down. So that would be the fade. Here would be a little bit below minus 45. Here would be below minus 90. And continue towards minus infinity. So it would be something like that. Okay, so that's our body plot. Well, the body plot contains all the information we need to do the C+ mapping for the Nyquist plot. Where are we at omega equals 0? Where is here omega equals 0? Here, where's omega equals 0? If omega equals 0, what's log omega?
1. Negative 1.
Thank you. Negative infinity. So we're all the way here. So, what do you have? Log AR is log of absolute value of 12, right? So, at omega equals 0, log AR is log of the magnitude of absolute value of 12, right? Which means magnitude of DOL is 12. What about phi? What's phi on this one? Read the graph. What's the value of phi? 0. And phi is 0. So where is that? Let's draw it here. So this would be, here is the real part of DOL of S. Here is imaginary part of DOL of S. We will start where? At 12 distance. Let's say here's 12 and angle 0. We'll start at this point. Everyone understands that? The body plot says the distance from the origin, which is the magnitude of the complex number, is 12 at omega equals 0, since it hits at log absolute value of 12. Right? And the angle is 0, so we're here. What happens now? Let's follow the white and the orange curves as omega increases. So omega increases, we move this way, right? So, notice, and I should have drawn this a little bit more accurately, this pretty much goes down slower than the phase lag. The phase lag starts going down almost immediately. The phase lag goes faster down than that you would see. So what you see is that the distance, remember, this is the distance from the origin. This is log of the distance from the origin. At the beginning, until the corner frequency, it doesn't go down. Oh, sorry, orange. This would be going slower. This is going slower. It would be more like this. Where's the corner? Well, wherever the corner is. So until the corner frequency here, until the corner frequency, this guy doesn't go down much. Here, look at this. Actually, this is the plot I should look at. This first of all, this is the one. So look at the orange. It goes down slowly until I hit close to the corner frequency. And phi starts going down before. Remember, at corner frequency, it's already minus 45. The orange line, the log AR, is the distance from the origin. So the distance of the origin goes down slowly. And I knew my laptop. So, the distance from the origin goes down slowly. Okay? But what happens to the angle? The angle becomes negative, right? And more negative. So, what I will say is, distance is pretty much the same. I'm pulling the limit inside the grid and the angle goes down. Once I hit the corner frequency, then it starts really being pulled in, while the angle starts going down a lot faster. So what will happen is, at the beginning it looks almost like a semicircle, and then to start pulling in. As I'm going down, the radius becomes smaller and smaller and smaller and smaller. Here's where I am at minus 90. Continue. Minus 180. Continue. Minus 270. Back here, minus 360. What do you think is that? It's a spiral. I should be seeing this picture. This should be my sequence. You see that? It's a direct consequence of this polygon. We start at 12,0, and we're moving in this direction, decreasing the angle, and of course, log goes to minus infinity, which means ambulance itself goes where? What's 10 to the minus infinity? 0. That goes to 0. Well, phi goes to minus infinity, continuous spiral, in the clockwise direction. Very important, you will need to know which direction is clockwise. Anybody here who is not comfortable telling clockwise from counterclockwise, don't be shy. If anybody is uncomfortable, and I've had 2 years ago a student, so much used to digital watches and sellers, but you guys are not longer learning properly what's clockwise and counterclockwise. So I will put in the exam on the screen so you can see which way is clockwise, so you don't mess this up, because it's going to be critical for the stability criteria.
You took off points for that person?
No, right. I'm saying I'm putting for the whole class to see it, but if you mess up the direction, yes, you lose a lot of points because you already mess up the stability criteria. So it's very important that we can tell clockwise from counterclockwise. All right. So that's the C plus. How about the CR? I won't do a mathematical proof for CR. But remember, I have radius goes to infinity. And I'm doing body plot of GOL, which is just polynomials and a delay.
So that was just C plus portion of it?
Yeah, that's the C plus part. S equals I omega. Right. This is our GOL of I omega. GOL of omega I is only for C plus. For CR, S is R into the I theta. And R goes to infinity. So that's the C plus. Everybody okay with the C plus? We are going to be basing the Nyquist stability criterion at the end of this talk, okay? We'll have the Nyquist stability criterion. That's where we're headed. Be patient. All right, how about CR? GOL of S is GOL of R e to the I theta. And remember, what is GOL? It's going to be a ratio of polynomials. And remember, the denominator polynomial will have higher degree than the numerator. So it's going to be an A, something like, okay, Bn S to the n plus B naught over an S to the n plus B naught e to the minus ds. Put, in other words, Bn R e to the I theta to the n power plus B naught over an R e to the I theta to the n power plus A naught e to the minus R e to the I theta d. And recall that M must be strictly bigger than M.
Oh, proof.
Without fine math, just common sense, R goes to infinity. Polynomial ratio, where the denominator has higher degree, and the thing S goes to infinity. What's the ratio of polynomials where S goes to infinity? And zero. And furthermore, e to the minus infinity here. What's that going to be? Also zero. So from every count, this means that GOL of S goes to zero. The whole infinite semicircle maps to at the origin. That's it. The Nyquist plot of the infinite semicircle is just the origin. To be precise, guys, it's actually a zero radius semicircle. Zero. Well, we'll be revisiting zero radius semicircles soon, guys, so don't laugh too much about it. So here we're dealing with infinite radius semicircles, zero radius semicircles. We're having a lot of fun. So you understand that the whole CR maps at the origin. With me? All right. How about? So we're done.
Yep, see you in
You
one
didn't
thing.
see R. We still have C minus.
Have a good week.
Ha ha ha. Okay. I'm not doing it again. Believe me. Okay, now we have C minus.
I tried.
S is minus omega I. So GOL of S is GOL of minus omega I. Or, let me rewrite the GOL of omega times minus I. How is GOL of omega times minus I related to GOL of omega times plus I? What's the difference between GOL of omega times minus I and GOL of omega times plus I?
What's the difference? What?
They're complex numbers, both of them, and we get,
Conjugate.
say it? Exactly. They're complex conjugates. It's complex conjugate. In other words, it's the complex conjugate of C plus. Okay? So, going back to our picture, and remember now you start at infinity, right? And remember, at infinity we were at AR0, right? At infinity, omega infinity, we were here. So we start from here, and it will be the complex conjugate. What's the complex conjugate? It's the mirror image with respect to the real axis. If I have this, the complex conjugate would be this. For this, the complex conjugate would be, start from here, let me draw it in a different color. My orange. I really remember. It would go